So last but not least, we have the random subspace selections. So the general idea is that we select S random subspaces having the target dimensionality out of the n over k many possible subspace candidates, and then we evaluate each of them. Yeah. So that of course only makes sense if n over k is so large that it is not feasible to compute all of them actually, or to evaluate all of them actually. So in that case, you just select randomly some of them, yeah, and try to get the best one. Again, that needs a quality measure for complete subspaces, of course. There's a trade-off between quality and the number of subspaces you select, so the number of S, the value of S. But very often it's a good alternative to forward selection if the quality measure is not monotonic, because then you cannot use monotonic things here. And there are different randomization approaches existing, which we will see in the next subsection in a minute. So, for example, genetic algorithms can be used to do the randomization a little bit better than just naive sampling. Or you can also use so-called feature clustering, which we will see, as I told you before, on the next subsection. So here are the subspace projection algorithms. Again, the general approach is that we will have the genetic algorithms and the feature clustering. Yeah. So the general approach of the genetic algorithms is, again, we want to search for random projections of a given dimensionality. So so how many of them are there? It's n over k. So if n is large and k is large, this number explodes. So just randomly search for them may be a good idea, but can you do the randomization a little bit more intelligent, a little bit more sophisticated? And genetic algorithms are good for that. Yeah. So genetic algorithms typically encode individual states in the search space. So actually solutions as bit strings, possible solutions as bit strings. We'll talk about the population of the current solutions. This is a subset of all possible solutions. So once again, the number of possible solutions is n over k, and we want to have the best one, but we don't want to explore all of them. So genetic algorithms just keep a subset of all those possible solutions. This is the current population. And then we have a fitness function, which is actually the quality measure for a subspace. And the algorithmic schema is that we will shuffle, so to say, the population. So as long as we are not convinced to have the best solution, so to say. Yeah. And the algorithmic schema for shuffling is we will try to find the best solution in the search space by mixing up the population and changing the population from each iteration to the next one. Yeah? And then we stop, for example, if the best solution of the current population is better, clearly better than the best solution of the previous population, and so on and so on. Yeah? So there are different possible stop criterion here. We can also just stop after a given number of iterations here. So each iteration manages a specific population, and in the next iteration, the next population is obtained from the previous iteration, so from the previous population, using mixing and changing. Yeah. So this is the idea of shuffling, of mixing and changing the population from one iteration to the next, and then we will see how to do that now. So operations on the population. The population again is the candidate subspaces, k-dimensional candidate subspaces. How can we create new candidates for the next population? So there are typically two operations. The first one is mutation. So one dimension in a subspace in the current population. So R is a subspace of the current population. We just replace one of the dimensions of R by any other dimension with a given likelihood. Yeah, so we just randomly replace that, and we can somehow control that with giving likelihoods to the dimensions. And then there is another operation, which is the so-called crossover, where we just combine two subspaces, R1 and R2, from our current population for the next population. That means we just unite the features, delete the redundant ones, of course, and also delete, in addition, random dimensions until the dimensionality is k again. Because if we just take the union of R1 and R2, we just get too many dimensions. First of all, we delete the redundant ones, and then we delete further random dimensions until we have again a k-dimensional subspace. Yeah, and from all those candidates, we select for the next population all subspaces having at least a quality of some percentage of the best fitness in the current generation. Yeah? Only those are copied in the next generation. So this is a kind of, the whole thing, I mean, genetic means we try to somehow, do it like the evolution, survival of the fittest. So those candidates that have a low ranking, a low fitness, a low quality will not make it, or will have a very small impact on generating candidates for the next thing. Yeah. But of course, there may be the case that some low quality subspaces still could be good candidates for mutation or crossover for really high quality things. So for that case, we have also so-called free tickets, which is additionally each subspace is copied into the next generation regardless of its fitness, regardless of its quality, with a given probability. So U, Y, and X are typically some parameters you can tune in your genetic algorithm schema. Yeah, there are many variants of this basic algorithm actually. So different operations, efficient conversions, for example, by using so-called simulated annealing, which just decreases the likelihood of those free tickets, so this U here, with increasing iterations, which may make sense. Yeah. So the whole thing is quite sophisticated, and usually is much better than simple random. Simple naive random picking, but still it's a kind of approximation. It's not a kind of approximation, it is an approximation, it is in heuristics, so it doesn't guarantee that it gets the best k-dimensional subspace with the best quality measure. So keep that in mind again. So the good thing is it can escape from local optima during the search, because of this free tickets and stuff like, and also because of mutation crossover, and very often it provides really good approximations of the optimal solutions. The limitation is that the runtime is not bounded, at least in the original schema. That is easy to fix in the first glance, but typically that comes to the cost with additional parameters, like the easiest fix is just run it k times, but k is another parameter which of course impacts the accuracy of the result. If k is too small, less good results. If k is too large, maybe good results, but again a very high runtime. And the second point on the limitation side is that the configuration typically depends on many parameters, and they have to be tuned in order to get good results in efficient time. And this is a kind of research by its own. So tuning genetic algorithms is quite costly in terms of computational costs. But worth doing it. So it's a task on its own, and can be quite nasty sometimes.